And then we took his construction and did a series of modifications. So in particular, we modified his technique to construct counterexamples to Eremenko's conjecture, or to show that wandering domains can form lakes of Wada for transcendental functions, or to construct what we call maverick points, which are points on the boundaries of Fatu components that have accumulation sets that differ from the points of the wandering domain itself. Then we generalize this for meromorphic functions, and we generalize it with Paso even further. And yeah, so this is like the fourth iteration of this construction. If you have not seen any of the 3 talks from me before, then don't worry. I hope I will try to introduce things from the beginning. Okay. So as usual, so for this talk, F will be always a transcendental entire function, and we define the Fatu set and the Julia set in the usual way. And Fatu components can be classified as periodic, pre-periodic, or wandering domains. So wandering domains are those Fatu components that are not eventually periodic. So when you keep iterating, you never return to a Fatu component where you were before. This is one of the easiest examples to draw. So if you consider this function without the 2π, then these black Fatu components here are immediate basins of attraction. So they are invariant basins of attraction. And then when you add, the Julia set is 2π periodic, and when you add 2π to the function, then they keep switching 1 to the right every time. So yeah, so in particular for this function, all these black sets are wandering domains, and in fact, wandering domains are the only Fatu components of this function. Okay, so given a Fatu component, we can consider the set of limit functions of the iterates of the function restricted to that Fatu component. And then, so this is just, okay, so a function is a limit function if there exists a subsequence of the iterates along which the iterates of f in that subsequence converges to this function locally uniformly on the Fatu component. So if we have an attracting basin, then there is only one limit function, which is the constant function equal to the attracting fixed point. And similarly for a parabolic basin, the only limit function is the constant equal to the parabolic fixed point in the boundary. If you have a Siegel disk, then limit functions are of this form, where phi is the Riemann map that maps it to the unit disk, and then you have a rotation of angle theta, and then you go back by the inverse of the Riemann map. So they are all possible rotations on the Fatu component. And then finally, if you have Baker domain, then the only limit function is the constant function equal to infinity. Okay, so what happens for wandering domains? If you have a wandering domain, then it turns out that all limit functions need to be constant. This is a classical result. And in particular, these constants need to be points in the Julia set or infinity. So throughout this talk, we denote the set of limit functions of a wandering domain by, as I said, a subset of the Julia set union infinity. So we want to, the point of this talk is to try to understand what this set can be. Okay, so again, as usual, we can classify wandering domains in these 3 types depending on their limit set. So we have escaping wandering domains if the limit set is just infinity. Oscillating wandering domains when the limit set has infinity and some other finite point. Or bounded orbit wandering domains would be the case that infinity is not part of the limit set of the wandering domain. Okay, so if you have multiply connected wandering domains, then Baker proved that they are always escaping. So for the purpose of this talk, the wandering domains that we'll be interested to look at will be the ones that are simply connected. And of course, one of the biggest questions on this topic is whether these bounded orbit wandering domains actually exist. This is not strictly related to the topic of this talk, but I wanted to mention this recent result by Leticia Pardo-Simon and Dave Sixsmith. So they constructed functions with entire functions with wandering domains such that they spend most of their iterates in some bounded set. So we don't know yet whether these bounded orbit wandering domains exist, but basically these wandering domains, you can imagine that there is like a repelling fixed point in the center of this disk. And then the wandering domains go to infinity, but then return deeper and deeper close to this repelling fixed point. So this means that it takes a lot of time for the wandering domain to actually exit again this disk, right? And this number of times that it takes to exit this disk is larger and larger compared to the time that they spend going to infinity. So yeah, I think of this as lazy wandering domains because they spend most of the time in this disk. Okay. So what are the other restrictions that we know about these limit sets on wandering domains? So Baker proved that the limit set needs to be a subset of the Julia set intersection, the post-singular set of the function. And then these 5 authors proved that, in fact, it needs to be as part of the accumulation set of the post-singular set. So that this is the derived set of the post-singular set, the set of all possible limit points of this set. But yeah, the main question we're interested in this talk is how large this set can be, okay? So yeah, there are several ways how we can measure if a set is large or not. So also, let me say that usually in all examples, so here I try to put maybe, it tries to be a complete list of examples of wandering domains that are oscillating. I apologize if I forgot any. So in these examples here, the limit set is countable. So it usually consists of the orbit of a point that escapes to infinity, or a countable union of orbits that escape to infinity, right? So this is the first example of an oscillating wandering domain by Rempe and Lubitz. And then there have been recently many more examples, but yeah. So then there was a question by John Osborne and Dave Sixsmith, which asked, is it always the case that this limit set is always countable? Can it be an uncountable set? And Kirill produced an example. I think this was part of his PhD thesis, where he obtained a function in the class B with an uncountable set of singular values. And for this function, the limit set of the wandering domain of the function contains the set of singular values. So in particular, this is an uncountable set. We also produced in 2022 an example with Lasse and James, where this has a wandering domain. This function has a wandering domain such that the limit set contains a union, countable union of unbounded curves. So it's not only uncountable, but it contains some continua. Okay, so I wanted to also talk a bit about, so I found this confusing in the beginning. So one thing is the limit set of the wandering domain, this set lambda UF, and a different thing is the accumulation set of the wandering domains as a set themselves, right? So if you define the omega limit set of a set X in this way, right, then the limit set of the wandering domain corresponds to this quantity when X is just any point of the wandering domain. But then you can also look at what happens to this if you put the whole wandering domain here. And then this is strict, it's like a larger set in some cases. So in particular, in the case that So you can imagine some set that is, for example, okay. So for this, imagine that you have a wandering domain that is escaping. So in this case, lambda equals just the constant infinity, but it could have a point in the boundary of this wandering domain that accumulates to infinity and another point. So this means that these wandering domains would be, so all points go to infinity eventually, but as a set, it sort of stretches so that part of the set accumulates to a point. So in this case, because this is an escaping wandering domain, so this set would be connected, and it would include this point that you're the boundary point is accumulating, and also infinity. So it would contain this unbounded curve. Okay, so yeah, as I said, in a wandering domain, when you look at just one point, so this quantity is the same for every point in the wandering domain, but if you look as a set, it may be accumulating to more points. Okay, so what did we actually prove about this? So this is the main theorem I want to talk today. So it says that if you start with any full compact set, then there is an entire function with such that every component of the interior of your compact set K is a wandering domain whose limit set is the Julia set union infinity. So as I said, this set here is always a subset of this. So in some sense, this is the largest possible set that you can hope for a function relative to the Julia set. We can then talk about whether this Julia set is large or small in several ways. But relative to Julia set, this is the largest that you can get. And yeah, I like the title of this talk and the paper, because so at the time that we proved this, Alex Eremenko was visiting Liverpool. And when we explained him this result, he just said like, oh, this means wandering everywhere. And I really like this expression. Anyway, so, okay. So what can we do with this? So in particular, we have this corollary because we have the freedom to choose the compact set that you start with. So if you choose a compact set that has a boundary which has positive area, then this will be a subset of the Julia set. So this Julia set will be large. So in particular, you can have wandering domains such that the limit set has positive area. So not only uncountable or contains continua, but it's much larger. Okay, so as I said, this construction, it builds up on several iterations and modifications of a construction that goes back to Bogthaler. Yeah. Yeah. So for this, you choose K to be a set whose boundary has positive area. So you could choose like one of these single disks with positive area or something. So then because every component of the interior of K will become a wandering domain, and its boundary will be part of the Julia set. So if you choose K to be like that, then it means that the Julia set of the function has positive area. Yeah.
Do you know what the singularities of this function will be?
I don't know what the singularities of this function. So this talk has a section at the end with lots of questions, and I think this is one of the questions. So yeah, all this is done using approximation theory. So yeah. Any more questions at this point? Yeah. So as I was saying, this builds up on a construction that started with Luca Bogthaler. I think how it goes is like he was working on similar things in several complex variables, and then realized that even the small question of can a wandering domain be a single disk, just like the unit disk? Can the unit disk be a wandering domain for some transcendental entire function? He didn't know. And then he developed this technique inspired by his work on several variables. So he proved that if you have a bounded domain that is regular, so regular means that, so this is not regular. Regular means that if you take the closure and then the interior, then you recover your set U. So if the domain is regular and satisfies that the complement of the closure is connected, so it's not like this, then this is enough to ensure that there is a transcendental entire function for which U is a wandering domain of this function. And by this, I mean the exact same set U. So you are able to fix exactly which set will become your wandering domain. It's not approximately or anything like that. And in his construction, he can also prescribe it to be escaping or oscillating. In particular, it follows from his result that every Jordan domain is the wandering domain of some entire function. Okay, so then we did a more general, slightly more general version of this result where so the proof is very similar, but the point of view is different because in Lucas construction, you start with the open set that you want to become your Fatu component, while in our result, you start with a compact set, and then it will turn out that the interior components of your compact set will be the wandering domains. Okay, so we start with a compact set, and then we obtain a transcendental entire function with these properties here. So the boundary of the compact set is a subset of the Julia set. The compact set K is wandering. So this is a version of what the wandering domain does, but for a compact set. And then, as I said, every component of the interior will become a wandering domain. And here I was a bit lazy. I just put that we can prescribe the limit set for every component of the interior. So this means that we can say, okay, I want this interior component to be escaping. I want this one to accumulate to these certain points, etc. Okay. So this is the improvement in terms of which wandering domains we can obtain from this. So in his case, he had these two conditions. So the first one is a necessary condition. So they always, so for two components, even for meromorphic functions, they need to be always regular. But the fact that the complement of the closure is connected, it's not the optimal condition. So we replace it by this condition, saying that the outer boundary of the wandering domain, of the domain U, needs to be equal to the boundary of U. Okay, so how does it look? So for example, you can obtain, this is the lakes of water that I mentioned before. So here, what you're looking at is like three planar domains, the blue, yellow, and black. And these three domains, they have the same boundary. So the boundary of the blue equals the boundary of the yellow set, equals the boundary of the black, and the boundary of the white unbounded set as well. Yeah. So this boundary, they share the same boundary, but they have different interior components. And we can have, there exist versions of lakes of water that have infinitely many domains sharing the same boundary. And as I said before, even in that case, we can prescribe that each of these domains can have a different limit set under iteration, despite they all share the same boundary. This is another example where the outer boundary equals the boundary of U. So again, these two cases are not covered by Bogtaler because if you take one of the domains and take the closure, then they disconnect the plane. In the complement, there are several complementary components. So if you do it for one lake, then all the other lakes and the unbounded component are all complementary components. Here, you would have the interior of the disk is one complementary component, and then this other unbounded component. So these are not covered by Lucas' result, but they are covered by our result. We are still separately working with Phil Gwyneth and Dave Sixsmith on trying to fight this type of domains to see whether they are actually wandering domains or not of some function. But this is not the topic of my talk today. So I want to go back to the talking about the limit sets. So I want to give a sketch of the proof. I thought that the best thing to do for this would be to follow this scheme. So first, I can do the idea for the construction where the wandering domains are escaping. Apologies if you have seen that already. Then I can discuss how to change it to make the wandering domain to be oscillating. And then as the third step, I can tell you how to change it again to make it not only oscillating, but make sure that it accumulates to every point in the Julia set of the function. Okay. So we'll do it in 3 steps. All these constructions use Runge's theorem as the machinery that provides your functions. So the way it is done is that the function you want to obtain is given by as the limit of a sequence of polynomials Fn that become closer and closer together on larger and larger sets. And these polynomials Fn, they are produced by Runge's theorem. So in Runge's theorem, you have some compact set K and the function defined, function phi defined on this compact set K. Then there is analytic on a neighborhood of K. And then given an error epsilon that you want, this theorem provides you a function, in this case, a polynomial that is epsilon close to your function that you prescribed on the set K. Okay, so we will be, it's a sort of iterative construction, and this sort of ideas date back to the time of Eremenko and Lubitsch of using Runge's theorem in an iterative way. Okay, so since you can choose your compact set K, I like to use Blood's rabbit as the example of a compact set K. So here throughout the talk, K will be this. So what we have, let me try to do it on the board. You don't need to probably read all the slides, but okay, so you have your set K, and then what you want to do is to obtain some sequence of full compact sets that approximate your set K. Okay. So you should, this gets closer and closer. Okay. Okay. And then the dynamics of the function will be as follows. So imagine that this is contained into the unit disk, and then you place next to it a sequence of disks. For example, you can translate them to the right. Okay, so the first function that you will construct maps all this yellow set. It will translate it to the right. So the translation, the map that you will prescribe in Runge will be just a translation. But if you're sufficiently close uniformly to this translating map, then the function produced by Runge will be still univalent. So here you will have some a little bit distorted version of your rabbit. Right, so the rabbit will look maybe a bit distorted. Okay, but the important thing is that you will have the same set that you have here will have moved to the right. So you will ask the function to translate this to the right. And then besides this sequence of domains, we will have another sequence of points. So in between each of these domains, we will place a point with a property that the limit of this sequence accumulates to all the boundary of K. Right, so these are the points Pn, which accumulate to the boundary of K. And then we have this sequence of Kns, which are full compact sets. This is a sequence of points. Okay, so at each step, at the first step, the function will translate this and will map this point into some, let's say we have an attracting basin here. We'll map the first point into this attracting basin. Okay, then we will approximate this function. And then in the second step, what will happen is that starting from the next level, so because this thing moved in a univalent way, the point that was here, now it's some other point here. So in this second step, this level will have moved to the right. Okay, and this point that started here moves here, then at the second step of the construction will map to the basin of attraction. Okay, and you can see how this continues. In the third level, this green set will move to the right. So if you are in the set K and you iterate the function, then you will always move to the next circle, etc. While the sequence of points that accumulates to the whole boundary of K, depending on how close at which level they are, they will move a certain number of times with the set K being translated to the right. And eventually they will sort of like peel off to go to this basin of attraction, right? So this means that for the resulting function, near these points, there is a preimage. So each of these points is contained in a preimage of this basin of attraction that contains this disk here, right? So for the resulting function, the boundary of K is accumulated by this other Fatu component. So it is clear that the boundary of K needs to be in the Julia set because each point in the boundary of K has preimages of a basin of attraction of different periods accumulating to it. So it cannot be normal. But then if you are in an interior component of K, you will just have been moved to the right every time. So you will be in the escaping set and you will be a Fatu component. Okay, so as I said, this is constructed as an iterative construction. So at each step, we do one of these steps. Okay, and then, so if we have done one step, then we draw a very large disk that includes everything we have done before and preserve. So at the end step, we preserve everything we have done until some stage, and then define the function on this new set here and a neighborhood of this point that we want to map. Okay, so at every stage, we will apply Runge to a very large circle that contains all the disks that we had until some point, plus this set in the next disk that contains the next level. So here the function will be just a translation. And on this neighborhood of this point that we have outside, it will be just a constant function, say the center of the basin of attraction. The idea of this is that if we choose the error in Runge's theorem sufficiently small, then all these things are preserved. You will still have a univalent image of this domain on the right. This point here, even if it moves a little bit inside this basin of attraction, if the error is sufficiently small, then you will still have the point. So the image will be different, but in the domain, the point will be the same. You will have a preimage of the basin of attraction here, etc. Right? So you can see how you can obtain this sort of escaping wandering domain by using these two auxiliary things, this approximation of the set K by full compact sets, and this sequence of points that accumulates in the boundary. Okay. Say now we wanted to do a version of this that is oscillating. So this already was done by Luca as well. So you can modify this construction. Maybe I'll try to do it here. So this will be the escaping. Okay. Are there any questions about the escaping construction before I moved on? Yeah. Okay. Yeah, probably I was too quick. If you find that you have any questions later on, let me know. Okay, so I'll try to draw it again. Okay, so again, we'll have compact set. And we use this sequence of approximating compact sets. Okay. And again, we put this inside the big disk. We consider the translates of this disk. So in the first step, again, you consider the translation to the right. But then the difference in this case is that instead of translating directly one more unit to the right, what you do is that you have a function already that moves this to here. So what you do is you send this level here to the next part. Let me think, is it inside or outside? So now you move, I think it's here. So you move it here. Okay, so this has moved here. Now you move it into this level. So because it's in this, inside the red curve here, and the function is univalent, so this function will move it back again to here. Okay. So now at this stage, so you move the orange thing that will be inside here to the right. So here you have the orange thing, the green, and the rabbit. Does it make sense? So in the previous one, we had the first level translate to the right, then the second level translates to the right again. Now what we do is, once we are in this stage, we send the next level to this part here, which was moving here. Now we move this here. So again, this next time we will send this. So until here, all the orange set arrives. So we need to send this inside the orange set. So say we put it here. Okay, and because this thing is a univalent map, we have a copy of this into here, which then again translates once more into here. And then the green part here is the one that we move to the right again. Okay. So these are the question.
So this small piece on the left, it's already sent to the right by the prescribed web, right?
Yeah, so here it's already, once it goes back here, we have already defined the map there. So it just moves along as whatever was to the right. So it's a univalent map. So we only have control at this stage that is sort of here, right? At some point, we keep everything we have inside. So outside, we have this next level and the point before. We send this to the right and this to the left. Here, what we have is something, say, until here. And now we have, we need to have this and the next part, I think. Something like this. We only have the new parts that we are adding. We cannot change the function where we already defined it in the previous level. So we just use it like as a taxi type of thing. Okay, and the important thing here is that the function is univalent. So you can track all the levels that you had approximating the set and you don't lose any of these properties. Okay, so until here, it's sort of familiar, I think, to most people that have seen me speaking before. So I want to talk briefly about what are the new things that we did. So how do we ensure that we guarantee that you're accumulating to the Julia set? And this at first looks a bit tricky because the Julia set depends on the function and you're sort of changing the function. So how do you know where you need to accumulate if you have not yet finalized the function? So the properties that we use is that repelling periodic points are dense in the Julia set. So in order to accumulate to the whole Julia set, we want to visit all repelling periodic points of the limit function infinitely often. So yes, and this sort of result ensures that if you visit the repelling periodic points of these maps Fn, and you keep increasing the period and the set where you look. So we don't accumulate to all repelling periodic points. We accumulated the repelling periodic points inside this big disk at each step where we can control the function. Okay, so I made a sketch. I didn't have the time to draw a proper sketch. So that's what we have. Okay, so here you can see there's a small rabbit. This is the wandering domain that was moving to the right, okay? This large disk represents the place where we have things built before. Okay, so here we have prescribed things before, and then as usual, we land here. So one difference is that we use, instead of using Runge's theorem at every stage, we can use Arechelian's theorem. So for each of the intermediate functions in this example, the wandering domains, they don't stop there. They keep moving always to the right. So this function has a wandering domain that starts here, and it goes here, it keeps moving to the right. What we want to do is, so we want to map some of the future image of the wandering domain into some neighborhood of the repelling periodic point, some set near the repelling periodic points that has the property that goes around visiting all repelling periodic points at that stage, and before we continue going to infinity. So at every stage, we do a small detour. Instead of just going to one place and then continue moving, we go inside, we visit all the repelling periodic points that we need to visit in a certain disk, and then we continue. So how do we construct this set we want to move to? So besides doing this wandering domain here, we can also make that the opposite sequence of disks are wandering. And then we have the Alford-Islands theorem that for an entire function says that if you take 3 domains, then at least one of these domains will have infinitely many preimages in a neighborhood of a repelling fixed point, so repelling periodic point. So we start with 3 domains. We know that for each of the repelling periodic points in here, one of them at least will have infinitely many preimages in a neighborhood. And then from each of these infinitely many preimages, we pick 3 of them, and then we take preimages under a certain iterate. It's not just f minus 1, it's iterated preimage. and then we go find another preimage near another of the repelling periodic points, and then we find another one, blah, blah, blah. So eventually we obtain this domain that if we map this into there, then it will visit the repelling periodic points until a certain period within this disk before going back here and then going to infinity. The reason why we need this auxiliary sequence of wandering domains is to ensure that there is the place where we are meeting, where we are mapping, has no Julia set inside. This is sort of a technical condition. But the idea is sort of simple. Instead of just going back and moving as usual, then when we enter here, we need to sort of do some homework of visiting all repelling periodic points. And then in the limit, the function will satisfy this property. So are there any questions? Yeah.
So the Rempe theorem would not be sufficient if you do like this on end step. If you're outside of your large disk, you can prescribe your map there any way you like. You can move your wandering domain close to any point you want, and then you just wait until you escape from large disk. Do this again.
I think the problem was that we didn't want to have Julia set in here. So when we take preimages of this, right, you need to make sure that these things do not mix with what you have of the wandering domain, because otherwise it could destroy what you had already. So that's why we created an artificial wandering domain, which is like a safe space for making sure that these domains here, they're all in the Fatou set, so we can map there and not mess up with the other. So it can, these sets here, I drew them like they can go around, but they need to be disjoint from the wandering domain because the wandering domain keeps going to infinity to the right. And these preimages of these domains do not do this because they move to the left. So these two things are disjoint. They may sort of separate like this. So it's a bit more technical. We need to consider a larger disk until all the preimages of this that we want are fully contained in that disk so that we don't mess up what we had already at that point. But then we move to the right. So that it might be just a cheap fix in a sense, but it makes it easier for us. I think the answer is I don't know if you can do the same with Runge's theorem. This is sort of easier. And
Another question. I don't know if you were answering, so I was not hearing you very well. So I don't know if I'm asking something that he already asked. So this construction allows you to accumulate on over every repelling fixed periodic point, and then by the density of those in the Julia set, you get the Julia set. But the construction allows you to control if you are accumulating to anywhere else or not.
No, but so here, because we are taking, it's not like the first preimage, it's like nth. So here, I think we're taking more than one preimage in each of the cases. So it could be that in between you have other sets. This is why I try to draw it like this. So you need to put all the sets where you're going, all these intermediate sets where you're visiting so that you're going to the repelling periodic points. You need to add them to the construction, but this is like a bounded set. There's a finite number of steps. You need to not change, you cannot change the function in these places. Does that make sense? So you need this set that goes around visiting the repelling periodic points, and sometimes it will not go to all the repelling periodic points and it will do other things, but you put everything in a very big disk and you move on from this. And you cannot change the function in these places. So this is why we had this bigger disk. Okay. So in the last 5-10 minutes, I wanted to discuss some further questions related to this topic. So one question we had is whether we can do this thing, but have no other Fatou components. So I forgot to mention, so in this left blackboard here, in the escaping case, we had these basins of attraction that are also Fatou components of this function. You can, if you want, replace this by some repelling periodic points and get rid of them. Here in the right, naturally, there are no other Fatou components because since the set is oscillating and the boundary can be accumulated by the preimages of the orbit itself, you don't need any auxiliary photo components. So yeah, this is one question we had, whether you can have like a wandering domain such that a function with a wandering domain says that the ground orbit of this wandering domain, the photo set consists of the ground orbit of the wandering domain and nothing else, and still accumulate to the whole Julia set. Like this is an example of a function for which the photo set is just the ground orbit of a wandering domain. Yeah, we don't know yet. Another question is, so I think I heard this question first from Nuria some time ago. So there's this result by Bergweiler, Haruta, Kretenmeier, and Terglen that says that the limit set of the wandering domain needs to be contained here, but actually in all examples that we know, it is true, this stronger thing is true, that the limit set always means the accumulation set of the singular values, the derived set of the singular values. So yeah, I think this is an open question relating this limit sets. Then, as Gustavo was saying before, we have no control about the singular set of this function. So one could ask, can you do this in the class B? Right? Is it possible for functions so the class B has no escaping wandering domains because the escaping set is a subset of the Julia set for functions in the class B. But as Bishop showed, they can have oscillating wandering domains, which are the ones that we are concerned for this talk. So can wandering domains in the class B accumulate to the whole Julia set? We don't know. As I said, this technique does not give us any control on the singular values. But maybe someone could use some surgery technique or something. Yeah. So this other question is about the relationship with, so these Maverick points, as I said, are points of the boundary of a wandering domain, such that the limit set or the omega limit set of these points differs from the omega limit set of the points in the wandering domain. So for example, the wandering domain is escaping, and this boundary point is accumulating to some finite point, or the wandering domain is oscillating with certain limit set, and this is oscillating also with a different limit set. So one question is, does there exist a function with an escaping wandering domain for which there is a point in the boundary whose limit set is the whole Julia set, right? So this thing of accumulating the whole Julia set is done by a boundary point in an escaping wandering domain. I don't know. Then slightly different one, does there exist a function with a wandering domain such that the limit set is of the wandering domain is the Julia set, but the boundary contains an escaping point? I also don't know. But yeah, so I just wanted to say there are lots of questions related to this, and yeah, thank you for your attention.
Your question?
Yeah.
So you said that you don't have any control on the singular set. So what kind of bad things can happen in your construction?
What bad things can happen? But I mean, like, aren't there these examples where every point of the plane is an asymptotic value or something like that? Like they're very bad. So it's not only about the critical values, but it's more like maybe the asymptotic values. But yeah, we have no control.
I mean, in your construction.
But I mean, to have like the function in the class B, you need to make sure that the singular values are bounded, right? So if you don't know where the singular values are, how do you set?
We are working in trying to see the question before this one, but not entire, but meromorphic. I think we can produce a function which is which has no any So the limit function of the wandering set is not accumulating at any point in the singular set, but it is transcendental. It is meromorphic, which is not an answer but a partial one.
It's not passive.